Hello everybody, I wanted to go over integration by parts, which is a popular integration technique. So the formula here is that the integral of u times dv is equal to u v minus the integral of v du. So this does it, but this is a little bit of a confusing formulation, although it's more popular. So let me just show you another version here. Supposing we have the integral of f of x times g prime of x dx. What the integration by parts formula says that this is equal to f of x times g of x minus the integral of g of x times f prime of x dx. Okay, so this is the formula, and the idea behind this is that you separate your integrand into two factors, one of which becomes easier when you differentiate, the other at least does not become more complicated when you integrate. And then you go over here, and because this guy gets simpler, this integral here should be easier than this one. So fabulous examples of using this formula U are stuff like inverse sine, inverse cosine, inverse tangent, the natural log, polynomials, because those become simpler when you differentiate them. Now over here your dv, or in this form your g prime of x dx, is stuff that doesn't become more complicated when you integrate it. So stuff like e to the x, sine x, cosine x, etc. Alright, let's do some examples. So for our first example, we have x times sine of x, and we would like to integrate that. Because x becomes simpler when you differentiate it, that is going to be a fabulous choice for our u. Because sine of x doesn't become any more complicated when we integrate, that is going to be our choice for dv. So u equal to x, and dv equal to sine of x dx. Okay, and then this implies that the derivative of u, which is du, is equal to 1 dx, and the antiderivative of dv is v, which is negative cosine of x. Now any antiderivative here will do, so might as well choose the easiest, which is where c is 0. Okay, so now using the integration by parts formula we have, this is going to be x times negative cosine of x minus the integral of negative cosine of x dx. Notice in particular that the x is gone here, so this is a substantially easier integral to handle. All that's left is to simplify this and integrate this guy. So this is going to be negative x cosine of x plus the antiderivative of cosine of x dx. And the antiderivative of cosine of x is sine of x. So this becomes minus x cosine of x plus sine x. And because this time we are looking for the general solution, we need the plus c. For our next example, I wanted to do the antiderivative of ln of x, which is actually a classic integration by parts example. So we're going to have u equal to ln of x, and we're going to have dv equal to 1 dx. This, of course, implies that du equal to the derivative of ln of x is 1 over x, and the antiderivative of 1 is, of course, x. Okay, now with this in mind, we can go ahead and use our formula. uv, so that's going to be, I'm going to switch the order, so it's going to be x ln of x minus integral of v, oh, excuse me, there should have been a dx here, v, which is going to be x times du, which is 1 over x dx. Okay, now we're in great shape because these cancel. And of course, the antiderivative of 1 is x. So this becomes x ln x minus x plus c. For my next example, I wanted to go over the antiderivative of x squared times e to the x. Now in this example, unlike in the antiderivative ln of x, it's pretty clear what your u and dv should be. In particular, u should be x squared and dv should be e to the x dx. The reason for this is that x squared becomes simpler when you differentiate. In particular, it becomes 2x, and e to the x doesn't become any more complicated when you integrate. So those are clear choices. But what makes this special, and the reason why I want to go over this, is because we're actually going to need to use integration by parts 2 times for this problem here. So let's get into it. We already said that our u is going to be x squared, and our dv is going to be e to the x dx. This, of course, implies that our du is going to be 2x And here the antiderivative of e to the x is e to the x plus c. And you see what we'll do, so we'll just choose 0. So v is going to equal e to the x. All right. So let's go ahead and do this. I'm going to put it over here because we're going to need the space here for the second by parts. So this becomes uv, so that's x squared e to the x minus the integral of 2x e to the x dx. Okay, and then I'm going to pull out the 2 here. So we have equals x squared e to the x minus 2 antiderivative of x e to the x dx. Okay, now we're going to have to use integration by parts on this fellow. Let's just go ahead and do that over here. So we have the integral of x e to the x dx. Now because x becomes simpler when you differentiate, that's going to be our u. And because e to the x doesn't become any more complicated when we integrate, that's e to the x dx is going to be r dv. Now this implies that du equal to dx and v equal to e to the x. Again, any c will do, so might as well choose the easiest. So therefore, the integral of x e to the x dx, this is uv minus integral of v du, which is simply dx. And we already did this up here. The antiderivative of e to the x is e to the x. Plus c. Okay, now let's go ahead and put that here. So this becomes x squared e to the x. Let me stand over here. Minus 2, and then I'll put parenthesis minus 2, and I'll put parenthesis x e to the x minus e to the x plus c. And then we can distribute the 2, and we end up with x squared e to the x minus 2x. Negative 2 times negative 1 is going to be plus 2 e to the x needs to be there, 2 e to the x, and then negative 2 times c. Since c is an arbitrary constant, negative 2 times c is still going to be an arbitrary constant, so I'm just going to do plus c. So this is our final solution to this problem here. For our next problem, I wanted to do the antiderivative e to the x sine x dx. Now this is an example where we have two terrific dv's and we don't have a good u. So what we do is actually we choose either of them for our u and the other one for our dv. It really doesn't matter. But what's going to happen is because these start repeating after the first iteration, we're going to do it again, and we'll actually end up with the same thing, and then we can actually add that to both sides. This is a little weird. That's why I wanted to show you. So let's just say, for the sake of argument, that u is sine x and dv is e to the x dx. Again, it really doesn't matter which one you choose for your u and dv. This, of course, implies that du is equal to cosine of x dx, and v is simply e to the x. Okay, so now let's bring this down here. So we have uv. I'm going to swap the order, which is totally valid because multiplication is commutative, so it's uv minus the integral of v du. All right, now we want to do this guy here using integration by parts again. This time we need to make sure to use the same sort of u and dv. U in this case is going to need to be cosine of x, and dv is going to be e to the x dx. If we did it the other way, we'd end up back where we started, which wouldn't be helpful. Okay, so let's go ahead and write it out. So u is going to be cosine of x, and dv is going to equal e to the x dx. This, of course, implies that du is equal to negative sine of x dx, and v is e to the x. Okay, so with that in mind, let's go down here. And then we have u, well, okay. So first let's just bring what we had before down. And then parenthesis here. So we have uv. So that's going to be e to the x cosine of x minus v. Du. Let's put the dx out here. All right, now we're going to go ahead and simplify this. In particular, I'm going to take the negative out here, and I'm going to distribute this negative here. And I hope you don't mind, we're going to do it in one step. This is easy. This is e to the x cosine of x with a minus in front. Now here we actually have a triple negative. Negative here, there, and here. So net that is going to be a negative, so it's going to be minus the integral of e to the x sine x dx. Now take a look. This is exactly what we got before. So what you do is you actually add this guy to both sides. Okay, so let me write this. We have integral e to the x sine x dx over here. And we go ahead and add this guy to both sides, plus integral e to the x sine x dx. And then over here, plus integral e to the x sine x dx. And when we get here, going over here, is 2 integral of e to the x, switching just to black, sine x dx equal to e to the x sine x minus e to the x cosine of x. Now, antiderivatives actually aren't necessarily unique. They're unique up to a constant, so when you add an antiderivative to itself, you end up with a plus c, not 0. So it's going to be plus c here. And then last step, go ahead and divide both sides by 2. And we get the antiderivative of e to the x sine x dx is equal to, dividing term by term, 1/2 e to the x sine x minus 1/2 e to the x cosine x, and then c divided by 2 is simply c. So this is just going to be plus c, and there is our final answer here. For my next example, I wanted to go over the antiderivative secant cubed of x dx. This one you actually do by parts, and you do that by breaking it up as follows. We have secant, let's do this, secant of x times secant squared of x dx. And you want to do this because the antiderivative secant squared of x is tangent of x. So u is going to be secant x, and dv is going to be secant squared of x dx. So therefore, du is going to be the derivative of secant x, which is secant x tangent x. So secant x tangent x dx, and v is going to be the antiderivative of secant squared, which is of course tangent x. Okay, so this guy here becomes uv, which is going to be secant x tangent x minus the integral of v tangent x du, which is secant x tangent x dx. Let's go ahead and simplify secant x, or tangent x, secant x, tangent x, that of course becomes tangent squared x, secant x. And then we have tangent squared x secant x dx. Okay, now you can go ahead and do by parts a second time to handle this, but there's actually an easier way, and that is to use a Pythagorean identity. Recall that 1 plus tangent squared x is equal to secant squared x. This implies that tangent squared x is equal to secant squared x minus 1. So instead of writing tangent squared x here, we're going to write secant squared x minus 1. And this is secant, let's use black. This is secant squared x minus 1 secant x dx. Okay, and then we're just going to distribute, and you see here one of the terms here will be secant cubed x, and the other term will be secant x. Secant cubed is the same as what we had over here, so we can just add it. Secant x, that's a tough one to remember, but it's actually one you're supposed to know. That's ln of secant x plus tangent x. So let's go ahead and do it. Secant x dx. Okay, and then we break this up into two integrals. So we get secant x tangent x minus integral of secant cubed x dx, and negative becomes positive. So let's do plus integral secant x dx. Okay, so now we add this to the other side, and we get that 2 secant cubed of x dx. We'll just switch to black is equal to secant x tangent x plus antiderivative of secant x dx. And I said before we needed the plus c because we still have an antiderivative. The plus c is sort of hidden away in here in some sense. So I'm going to go ahead and integrate this guy, and the plus c is going to show up. So secant tangent x plus ln absolute value of secant x plus tangent x plus c. And then last step, we divide by 2. And we get the antiderivative of secant cubed x dx is going to equal 1/2 secant x tangent x plus 1/2 ln of secant x plus tangent x. And because an arbitrary constant divided by 2 is still an arbitrary constant, it's still going to be plus c. So there's our answer. For our last example, I wanted to do the integral of arctangent of x dx from 0 to 1. I wanted to do this example because we had not done one with bounds of integration in this video. Now, the actual idea behind handling the antiderivative is very similar to ln of x problem that I had already done. In particular, u equal to arctangent of x is a fabulous choice because the derivative of arctangent x is easy. Now, less clear is what your dv is, but much like last time, dv equal 1 dx is just fine. Okay, so let's jump into it. So u equal to arctangent of x, and we have dv equal to 1 dx. The derivative of u here is equal to 1 over 1 plus x squared dx, and the antiderivative of 1 is simply x. Okay, so now this comes down, and we have uv, so that's going to be x arctangent x. Now, because we have bounds of integration, we do bar 0 to 1 minus the integral of v du, and this integral here is from 0 to 1. Okay, so now we can either wait to plug this in, or we can do this now. Let's just do it now so we can get it out of the way. We plug in 1, this becomes 1 times arctangent of 1 minus 0 times anything is simply 0, so this is going to be minus 0. And then over here, we have minus integral 0 to 1 of x over 1 plus x squared dx. Okay, and now arctangent of 1 is pi over 4. 1 times pi over 4 is simply pi over 4. So we have pi over 4 minus the integral from 0 to 1 of x over 1 plus x squared dx. To handle this antiderivative here, we simply use a substitution technique. So we're going to let w equal 1 plus x squared, which implies dw equals 2x dx. And so this guy here because we need a 2, I'm going to put a 1/2 out here. And this is 0 to 1. So this is the same as 1/2 integral. There's our dw right there. And of course the bottom is our w. Now, if x is 0, w is going to be 0 squared plus 1, which is 1. If x is 1, w is going to be 1 squared, which is 1 plus 1, which is 2. So this becomes 1/2 ln of the absolute value of w from 1 to 2, which is 1/2 ln of the absolute value of 2 minus 1/2 ln of the absolute value of 1 . This simply becomes ln of 2. Absolute value of 1 is 1, ln of 1 is 0, so this is going to be minus 0. So going back here, this becomes pi over 4 minus 1/2 ln of 2. Okay, thank you guys so much for watching. I hope you enjoyed the video.